Hey guys, so today we're going to be doing the third set of notes from the epidemiology unit. So in this case, we're going to be talking about cause versus correlation. And so let's begin. This is going to be a pair deck, so make sure that you cover the link in the materials folder to get access to the actual pair decks where you can write in your responses. So this first question is, what is a disease factor or health statistic that you know of? So for example, and don't use these examples as yours. So one example would be like smoking causes lung cancer, or flus happen mostly in the winter, or blue algae blooms kill dogs. So what's another disease factor and the disease that it's actually correlated with or causes? The next question on the pair deck is, how did that fact become known? So how do we know that that smoking causes lung cancer? Who came up with that idea? How did they explain that idea? How did they determine that cause and correlation? The next question is, how can we prove what is causing a disease? So let's say we have reason to believe that X factor causes Y disease. What can we actually do to prove that that is happening, that that actually has a causation, a cause and effect relationship? Here are 3 graphs, and on these graphs there are 2 types of occurrences that are happening. One is in red, the red line, one is in black, the black line. So just looking at this data, and this is over time, the x-axis would be time, the y-axis would be the number of occurrences. And again, these are of 2 different types of things. Based on the data that you're seeing in these types of graphs, what can you conclude between occurrence type red line and occurrence type black line? So then you're just going to fill out your answers there. Now here are the actual x and y axis and the title described for those particular graphs that you just saw, at least a couple of them. So the first graph that you saw was actually looking at the letters of winning words in the Scripps spelling bee, the number of letters in the words of the Scripps spelling bee, and the number of people killed by venomous spiders year after year. The second graph is actually looking at the per capita, so per population cheese consumption, amount of cheese consumed per person. And it's compared with the number of people who died by becoming tangled in their bed sheets. All right, so that's actually what those charts are really showing. So here's a quick question. Does the number of spelling bee letters cause people to be killed by venomous spiders? So we're going to be looking at this term cause. What in the world does cause mean? And then we'll also look at a term called correlation. What does that term mean? So to describe this, I'm going to show a short video.
Like most people, I enjoy a tasty scoop of ice cream, especially Oreo blizzards. But what few people realize is how dangerous a treat ice cream has become. First, there's the issue of obesity. Second, there are higher crime rates. Third, there's the loss of life due to a rise in the number of drowning deaths. And finally, as more ice cream is sold, there's an increase in forest fires. Given these indisputable facts, I need you to support my vision of an ice cream-free world. While banning ice cream trucks from entering your neighborhood may sound far-fetched, when it comes to problem solving, a common issue is misunderstanding the difference between correlation and causation. This misunderstanding can influence our decisions, sometimes with serious consequences that ripple throughout a community. Correlation is when 2 things are related, but one does not cause the other. Usually this means the 2 are in some way related to a third factor, but not always. If you have a big enough pile of data, you can find plenty of relationships that are purely coincidental, like the strong relationship between the sale of margarine and divorce rates in the state of Maine. With the sale of ice cream, the third factor is weather. When it is hot outside, people buy more ice cream. They are more likely to go for a swim, and there is a general increase in people out and about enjoying the weather, helping improve conditions for crime to take place, as well as the dry conditions associated with forest fires. A note of caution: there is a growing trend in our digital world called data dredging. This is using analytics to sift through mountains of data, hoping to find useful relationships. Instead of a problem in search of a solution, dredging data is a solution looking to find a problem. All of what I've just discussed about correlations does not mean that finding a correlation is without value. In fact, correlations are a vital part of helping us move to the next step, the discovery of causation. Unlike correlation, causation is when you can claim that one thing causes another thing to happen. In order to make this claim, you need to be able to demonstrate an actual cause and effect relationship, preferably a strong relationship. An example most of us are familiar with is the pharmaceutical industry. In order to make the claim that a particular drug causes a certain effect, such as lowering your cholesterol or growing hair, the FDA requires companies support those claims, putting the drug through a 4-phase, 12-step process that takes approximately 12 years. This process uses control groups and clinical trials to test the drug, making sure that X causes Y and that the drug is safe. The acceptable error rate can go as high as 5% for some drugs, meaning that the clinical trials prove that there's a 95% chance the drug does what it claims. Drugs with serious health implications, such as those used to treat a heart condition, are held to an even stricter standard, requiring proof up to 99% effectiveness. Back to ice cream. What about ice cream and obesity? While it may seem like common sense that it does cause obesity, the fact is that we don't yet know the true strength of the relationship. If we look at the sale of ice cream, there's actually an inverse relationship with weight. People gain weight in the winter when sales are low and lose weight in the warm summer months when more ice cream is being consumed. This might suggest ice cream is the new diet food. Luckily, you now know to be cautious of drawing conclusions of causation from correlation. Instead, recent research on the subject has been looking at different types of sugars used in making a wide range of sweet foods. What scientists have discovered is that the hypothalamus, which is an area of the brain that regulates the human appetite, reacts differently when we consume foods with fructose instead of glucose. This has researchers speculating that eating high fructose foods, such as ice cream, may result in people not feeling full, so they continue to eat. This theory proves difficult, however, when we start considering apples and other natural fruits also contain fructose, not just ice cream and chocolate cake. As you can see, causation is quite a bit different than correlation. Finding correlations is easy, proving causation is hard. No wonder it takes 12 years just to prove that a pill causes hair to grow. The bottom line, on the news, in boardrooms and coffee shops, everywhere you go, you will hear claims that X causes Y. From politics to the weather, from the stock market to personal relationships, it is human nature to try and explain things, to create stories that make sense. Just keep in mind, as you hear a claim of what causes what, that correlation is not causation.
All right, so that was a good descriptor for the differences between correlation and causation. So if we go back to our map, our graph, let's talk about that third option that was on that graph page. This graph actually was showing the number of people who drowned by falling in a pool with the number of films that Nicolas Cage had appeared in year after year. And if you see, we have really similar numbers. The increases, the decreases, the leveling out, they kind of happen in the same year. So does that mean that Nicolas Cage causes drownings? Well, no, that would be ridiculous, right? What we do see is a correlation between Nicolas Cage films and numbers of drownings. So that's a correlation. Correlation and causation are two very different things. Sometimes correlations can help us understand a little bit more, and sometimes it's just coincidental, like in these situations with these graphs.
Like most people.
So again, here's another graph. This is showing polio rates and ice cream sales. And so we see that the trends tend to be similar. When they go up, the other one goes up. When they go down, the other one goes down. Now, is that causation or correlation? So in this paradox slide, you're going to be drawing the icon or dragging the icons into the appropriate empty boxes. So the red is going to indicate causation, the blue is going to indicate correlation. So again, just drag the icon, red being causation, blue being correlation, into the empty boxes that are on this slide. So I want to bring in a third word here, a third vocab term. So we've got causation, we've got correlation, and now I want to introduce confounding. So causation is X causes Y. Correlation is two things have a similar trend. Maybe they go up together, maybe they go down together. There's a relationship between them possibly, but it's not a direct causative relationship. Confounding is another term. Now, confounding can kind of complicate things. So there is, if you click on this site, this link, it's going to bring you up to a page that talks a little bit more in detail about what confounding is. So click on that, read through it, and then come back to this page to answer the question. And the question is, in the example on the left, what may be the confounding factor when assessing the relationship between swimming, ice cream, and polio? Okay, so what's the confounding factor when assessing the relationships there? All right, so here are just a couple bits of information about how we can determine causal mechanisms. So how do you know that X causes Y? So let's talk about the polio study that we were just describing. Assume you're in charge of a case study. How would you go about proving that swimming, but not ice cream, is actually causing polio? So what would you actually do? How would you test this? So you're going to write in your answers there. In 1964, the Surgeon General issued a report, and it was talking about how we can determine some of these relationships and how we can do clinical trials and use basically experimental data. So observational trials and clinical trials we'll talk about, or experimental trials, we'll talk about the differences in our next class. So epi-data must be coupled with clinical, pathological, and experimental data. It has to consider multiple variables. Multiple studies need to be considered, and then statistical methods alone can't establish proof. We need more. If we go back to John Snow, here we go with understanding causal mechanisms is essential for effective public health intervention. Considering the case of miasmas and cholera, so again, that bad air concept in cholera. For want of knowledge, efforts which have been made to oppose cholera have often had contrary effect. So again, we need to establish good data and understanding of that data to really come up with a good causal explanation. What causes what? There's a Bradford Hill criteria meant to describe how we know and how we can use causality, how we can determine causality. Click on this article, and it's going to give you basically an overview about these particular criteria. And then for this question, you're going to determine, according to Rothman, the only criteria that is truly a causal criteria, according to Rothman, is what? And so these are the 8 criteria according to the Bradford Hill criteria. The strength of the association. The stronger the association between a risk factor and outcome, the more likely the relationship is to be causal. Consistency of findings. Have the same findings, have they been observed among different populations in different areas, among different study designs? Basically, is it consistent? Specificity of the association. There must be a one-to-one relationship between cause and outcome. Temporal sequence of association. The exposure has to precede the outcome. So you don't have the outcome before the exposure happened, right? You have to have the exposure and then the outcome. So you don't get lung cancer and then start smoking, right? It's people that start smoking, then develop lung cancer. Not if you've developed lung cancer, then we track you and see if you start smoking. That's it, describing the temporal sequence of association. It has to be exposure precedes or comes before the outcome. Biological gradient. Changes in disease rate should follow from corresponding changes in exposure. So kind of like a dose response. So more smoking causes higher rates of lung cancer. Even more smoking than that causes even higher rates. So basically there has to be a gradient, so corresponding changes in exposure, sort of like a dose response. Biological plausibility. Presence of potential biological mechanisms. What exactly is happening in the body to cause that effect? Coherence. Does the relationship agree with the current knowledge of the natural history and biology of the disease? Does it agree with other findings about that particular disease? Is it consistent with those other findings? Experiment. Does the removal of the exposure alter the frequency of the outcome? If somebody is not exposed to nicotine and they don't smoke, do they have the same frequency of lung cancer? Okay, so we would actually do an experiment to determine those things. We wouldn't force people to smoke, but we would look at existing data. So you're going to define these terms: cause, correlation, and confounding, and give an example of each of them. And those are the notes for today. So hopefully that helps to describe a little bit more detail what causation is, what correlation is, and what confounding variables are. All right, for the rest of today, you are going to have a short assignment, and I will open up that assignment and explain in just a minute what that is going to be. All right, so you are going to be completing this geographic information system, or GIS, and disease mapping activity. So it has a lot of background information. Try not to get overwhelmed by the introduction here. This is giving you just some background information about what these geographic information systems are and what disease mapping is all about. So you're going to read through the background information on here. Then what you're actually going to be doing is you're going to be looking at some maps of disease trends and disease factors and see how they correlate. So if you click on the first link, and I'll show you this. You're actually going to be clicking on the link. Then you're going to click on Interactive Atlas of Heart Disease and Stroke, that icon. Then you're going to launch the US map, the county level. You're going to select Texas, heart disease and stroke data, then total cardiovascular disease, 2016-2018 deaths. And I'll show you how to do that in just a second. Okay, so if you click on that link, it's going to bring up the CDC Maps site. And then if you go down where it says Interactive Atlas of Heart Disease and Stroke, click on that. Then you're going to go down to where it says US Map County Level. Click on that. Give it a second, sometimes it takes a minute to load. Once this opens, then you're going to want to click on Texas. So if you click on this drop-down menu, once it's loaded, and then you're going to go down to where it says Texas. Then you're going to see where it says heart disease and stroke data. And then under that, if you click on that, it should drop down this set here. You are going to click total cardiovascular disease. And then you have the option to click deaths, hospitalizations, hospital discharge statuses. So let's go ahead and click deaths. And we're going to choose an age range. So let's choose under age 75. We're looking at all deaths, both genders, all races, and this is going to be between years 2016 2018. So there's a bunch of years. We're going to go with the most recent. Click Apply Filters. Then it's going to bring up basically, this is categorized by county level. And so you can see that the more prevalent, the darker red it is. And so I'm going to zoom in a little bit so that you can click on where Williamson County is. So Williamson County, and if you hover over it, it usually tells you, if you click on it, it usually tells you what that is. Williamson County is sort of towards the middle of the map. Let me zoom out so you can see where we are. Here's Williamson County. It has that little kind of edge at the bottom that kind of goes into the one below it. So that's Williamson County. In fact, if you click on it, it brings it up. The one below it, just for your purposes, is Travis County. Okay, that's where Austin is. So we are in Williamson County. And then if you have clicked on that, you're actually going to see the rate per 100,000. All right, so if you go back to your assignment, it's actually going to ask for that information. It's going to ask what the rate in Williamson County is, and it's also going to ask, if you just look at the map as a whole, where are the highest incidences? Where are the darker areas for deaths due to heart disease or cardiovascular disease? All right, so you're going to continue doing that, answering the questions on the document as you go. If it's in italicized, it tells you basically you're going to be changing one of these filters. So for example, the next filter is going to be 65 and over. Looking at deaths, we're going to apply filters and then see how that affects our data. We're going to then change maybe races and ethnicities. So let's choose Black or non-Hispanic. And then we have those rates. You can do the same thing with other races, ethnicities. All right, and so you're going to basically be seeing what the data says based on each of these subcategories. So they also have this based on males and females. They've got this age. They have the different races and ethnicities, and just you want to keep this unsmoothed. That's probably the best way to view this information. All right, if you need to then reset the whole map, it's this little kind of half circle icon, this little backwards arrow. Click Reset Maps, and it brings you back to the option where you can check other things like the risk factors. So if we wanted to look at, let's say, obesity, we would click on that, obesity percentage, and again, it breaks it down, the prevalence or obesity percentage and prevalence of based on the counties. All right, so that's how you're just going to be answering questions, following the instructions on the worksheet, answering the questions as you look at that different data. Okay, I'll see you all next class.